to be treating past question, right? The past question on what we've done on fluid mechanics. Okay, the question says that the space between two square flat parallel plates is filled with oil. Each side of the plate is 720 mm. Full stop. The thickness of the oil film is 20 mm. The upper plate, which moves at 3 meters per second, require a force of 140 Newton to maintain the speed. Determine number one, the dynamic viscosity of the oil. Number two, the kinematic viscosity of the oil if the specific gravity is 0.90. Alright, with this data, we have to solve the dynamic viscosity and kinematic viscosity. First thing first, list out your parameters, right? Now, let's list out the data. Given data, we are given each size of the plate, right? Let's denote it as x, meaning x is given to be 720 mm. So x means the size of the plate, each size of the plate, 720 mm. We're also given the thickness of the oil. By thickness, meaning dy, thickness dy is given to be 20 mm. The velocity that drags the upper plate, we are given velocity. Let's denote the velocity as u, 3 meters per second, and the force required to maintain the speed, that's 140 Newton, right? We're also given specific gravity of oil. Specific gravity 0.90. Alright, with this, I would love us to draw the schematic illustration interpreting this question. The question says that a parallel plate, right? This is the first plate, this is the second plate, this is the lower plate, and it is fixed, while this is the upper plate. Then the distance, this plate is filled with oil film. Let's say we have our oil film like this. This is the oil film. Oil film. So this is the oil film, right? Now, the thickness between the upper plate and the lower plate. The thickness between the upper plate and the lower plate, meaning dy. And from here, we said dy is equals to 20 mm, right? The upper plate requires a speed of 3 meters per second to maintain a force of 140 Newton. Meaning at this place, the plate started with 0 meters per second. The velocity of the plate initially was 0. So we have u here to be 0 meters per second. 0 meters per second. Then the u here to be 3 meters per second. Right? The force required, let's say this, we are giving the force of 140 Newton. Then the question also says that the size of the plate is 720 mm. Consider this. This is a square, right? All this A, B, C, D. You agree with me that AB is equals to CD. Likewise, AC is equals to BD. So same idea. If you call this place X meter, it means this place is also X meter. Likewise, AC represents AC as L meter, meaning BD is also L meter. So that's this idea that we are implementing here. Since the question says that a square plate parallel from each other, meaning the size of the plate here is 720 mm. 720 mm. Similarly, the size here is also 720 mm. So this is the illustration for the question. Alright, with this, let's solve the first question. calculating the dynamic viscosity, also calculating the kinematic viscosity. We call shear stress is equals to your dynamic viscosity. Your shear stress is equals to the product of dynamic viscosity times the velocity gradient, du over dy. Call this equation 1. From equation 1, make dynamic the subject of the formula, or better still, substitute substitute the value of each parameter into equation 1. But for a nicer calculation, I would make this the subject of the formula. Meaning, by doing so, it means that your dynamic viscosity is equals to your shearing stress multiplied by dy divided by du. Call this equation 2. Alright, to obtain the value of dynamic viscosity, we need our shearing stress, meaning shear force, right? Here we need our thickness. We also need the change in velocity. Now let's calculate. From the parameters highlighted from the question, there's nothing like shearing stress, right? Or shear force. Now we need to calculate our shear force. By formula, what is shear force? Shearing stress, or you say your shearing force, is given. Shearing stress is equals to force divided by area, meaning equation 3. So with this equation 3, you'll be able to calculate the value of the shearing stress acting on this fluid, right? Now dy, let's solve the value of dy. We are given dy. Dy is known, right? We know the value of dy to be 20 mm. What about du? The change in velocity. The change in velocity simply means the final velocity minus the initial velocity. That is, change in velocity du is equals to 3 meter per second minus 0 meter per second, which is equals to 3 meter per second. So what we are here to know is the shearing stress. We can use equation 3 to find that. Okay, now we know the force to be 140 Newton. How do you get the area? Here's the idea. Recall earlier that the question says that each side of the plate is given to be 720 mm by 720 mm. Meaning, to get the area, you simply multiply the length times the breadth. Consider this. Let's say we have A, B, C, and D. Cause CD the length and this to be the breadth. It means that 720 mm by 720 mm will give you the area. So by doing that, but in this case, you need to convert to meter. Our parameters are in mm, meaning we are converting to meter. So let's do that. From here, converting this to meter, this becomes 0.72 meter. Converting dy to meter, 0.02 meter, right? So therefore, area is equals to 0.72 multiplied by 0.72, which is equals to 0.514 meter square. Alright, let's substitute the value of the force and area into equation 3. Then from equation 3, we have that shearing stress is equals to the force, which is 140, divided by area, 0.514. Then this gives us 270.06 Newton per meter square. This is the shearing stress acting on the surface of the fluid. Substituting the value of the shear stress, the thickness, and the change in velocity into equation 1. That is, recall from equation 1, we have dynamic viscosity is equals to shearing stress times thickness divided by the change in velocity. So therefore, the dynamic viscosity becomes the product of shearing stress times thickness, meaning 270.06 multiplied by your thickness, that's 0.02 divided by 3, right? And this is equals to 1.8004 Newton seconds per meter square. So this is your dynamic viscosity, right? This is question 1. Now for question 2. Question 2 says that calculate the kinematic viscosity. How do you go about it? Recall your formula for kinematic viscosity. In the introductory video, I explained the concept of kinematic viscosity, right? The relationship between kinematic viscosity, dynamic viscosity, and density. So that's what we'll be using here. Now, for your question 2, your dynamic viscosity is symbolized with this, and it is pronounced nu, right? Nu, it is pronounced as this. From here, your kinematic viscosity is equals to your dynamic viscosity divided by density. We've obtained the value of dynamic viscosity to be this, right? Now, the question is, what is my density? Here, from the parameter we listed so far, we don't have anything like density, meaning I'm to calculate for density. Recall, what's the formula for density? Density is equals to mass over volume. But in this case, there's nothing like mass, neither volume. Hence, this formula won't be used, right? Notice that we are giving specific gravity. Why are we giving specific gravity? Specific gravity, we are giving specific gravity so as to calculate density. How? We call the alternative formula for density. And this formula is the specific weight of liquid is equals to density times gravity. Meaning from here, make density the shortest of the formula. Then density becomes specific weight of liquid divided by gravity. So therefore, as far as this question is concerned, this is the formula I'll be implementing for density. Now, how do I get the specific weight of liquid of water? From specific gravity is given by specific weight of liquid divided by specific weight of water, right, of pure water, where this has its value, a constant value, and that's 9810 Newton per meter cube. So therefore, make this the surrogate of the formula. That is, you are cross multiplying, meaning that specific weight of liquid is equals to specific gravity, and what the value? 0.90 times specific weight of water, that's 9810 Newton per meter cube, and this is equals to 8829 Newton per meter cube. With this, let's calculate density. Then density is equals to specific weight of liquid divided by gravity. Substitute. That's 8829 divided by gravity. Take gravity to be 9.81. Of course, by the time we divide, the value becomes 900. What's the unit of density? Mass over volume, kg per meter cube, right? So you have kg per meter cube. So this is your density. With this, you already know dynamic viscosity, and you know. So therefore, your kinematic viscosity nu is equals to the ratio of your dynamic viscosity 1.8004 divided by your density, that's 900. 0.0020, right? And what's the unit? Don't forget your unit. Meter square per seconds. For your dynamic viscosity, the unit is Newton seconds per meter square. But this, you have meter square per seconds. Let's see how this unit works. For the first one, dynamic viscosity, we come from your Newton's law of viscosity that states that your shearing stress is equals to your dynamic viscosity multiplied by du over dy, meaning velocity gradient, right? Now, make your dynamic viscosity the subject of the formula. It becomes dynamic viscosity is equals to your shearing stress divided by du over dy, right? Now, let's write dynamic viscosity in terms of units, right? Now, what's the unit for your shearing stress? Shearing stress is equals to force over area. Your force over area. And force is measured in what? Newton, right? So Newton per, what about your area? Meter square. Length times breadth, meter square. So this is your unit for your shearing stress. What about your du dy? Du over dy. Your velocity gradient it is the reciprocal of time, meaning that 1 over x. Time is measured in seconds, 1 over seconds, right? So therefore, writing your dynamic viscosity in terms of units, it becomes dynamic viscosity is equal to your shearing stress in terms of unit, Newton per meter square, meaning Newton per meter square divided by dy du, velocity gradient, 1 over seconds, right? Now, by that we simplify further, this is telling you that Newton per meter square divided by 1 over s. Of course, division will change to multiplication, the idea of algebra. Then it becomes Newton per meter square multiplied by seconds over 1. It means that your dynamic viscosity is equals to the product of Newton times seconds. What do you have? Newton seconds, right? Divided by the product of meter square and 1. That's meter square. So that's the unit. That's why we are using Newton seconds per meter square, right? Don't forget that. It is very important because in engineering generally, when you are working and you got a value without unit, that value is irrelevant. That value is not meaningful. That's what it means. So we come to the end of this video. If you find this video helpful, interesting, give it a thumbs up, encourage our channel by subscribing, sharing to your friend as well. See you in our next video.